Hello everyone. Today we are going to talk about subspaces, which is section 4.2. So we are going to start with definition. What is a subspace? Well, imagine that we do have a vector space V, and we do have two operations in it, like, addition and scalar multiplication. I put them in circles to show that they are not supposed to be regular addition and multiplication. They can be something else. Imagine that we do have a subset W in that set V, and this subset is a vector space by itself under the same operations as V. So these operations are the same, so it's not like different operations. And it's making a vector space, which means that it satisfies 10 axioms under same operations, and it sits inside of V. Then we are going to call it subspace. Some example of subspaces. Well, I'm going to just give one example. Example number one. Imagine that we have a two-dimensional plane and all possible points on two-dimensional plane. Like I'm going to draw like this coordinate space, and all possible points with coordinates x and y are going to make like R2, right? They're vectors in two-dimensional space, or just like points with two coordinates. Now, if I draw a line in this two-dimensional space which goes through origin, this line is going to make a subspace, and all points on this line, which are going to sit anywhere, are going to create a subspace. We can check literally axioms, but I'm going to just check two basic axioms maybe, or four basic axioms. First, is this subspace closed? If I take two vectors along this line and I add them or subtract them, I'm still going to get a vector along this line. I'm going to just make a drawing. Imagine that I have one vector and another vector probably goes the opposite direction. If I add them, I'm still going to get one point or one vector along this line, right? If I multiply a vector by a constant, I'm still going to get a vector along this line. So the space is closed under addition and scalar multiplication, right? Well, all arithmetic for vectors is going to work normally, because it's working for a parent space. So all arithmetic properties like scalar multiplication and addition are going to be inherited. Means that that's going to be addition is going to be commutative and associative law is going to work. Only two more axioms we will probably need to check are zero axiom and inverse axiom. So, well, kind of zero axiom is easy to check. For parent space, zero is actually what? It's a zero vector. It's a point with 0, 0 coordinates. Because the same point belongs to this line, it's going to make a 0 for it too. What is going to be inverse? Well, we know that for any vector on a line, we can build a vector in opposite direction, and if we add them, we are going to get 0, so inverse also checks. So basically all 10 axioms are working, and that's going to make a subspace. Now I'm going to give example of non-subspace, so you see that not all subsets or sets inside of space, vector space, are making subspace. I'm going to still consider R2 a space of two-dimensional vectors or pairs of points. Imagine that I'm going to consider 1/4 of this space. Points where x is greater or equal than 0 and y is greater or equal than 0. Is it going to be a subspace? Well, who knows? Let's check. I'm going to see that mostly addition of two positive 2 points inside is going to produce a point inside. How about multiplication? Is space going to be closed about scalar multiplication? Imagine that I take a point which belongs to this quadrant and it has two coordinates x and y, both are greater than 0. And I multiply it by -1. which is like any real number, right? And that's a scalar multiplication. What I'm going to get? I'm going to get negative x and negative y. And if we look at them, we are going to obviously see that point is going to belong somewhere here. So for the point which belongs somewhere here, I'm going to get a point which belongs here, which is outside of my space. So this subset is not closed under scalar multiplication. So not a subspace. Okay. What else do we need to know about subspaces? Well, interesting, guys. If you do have two subspaces and we do have intersection of them, imagine that we have a bigger space V, and there are two subspaces there, W1 and W2, and they intersect. Intersection of these two subspaces is also going to be a subspace. Why? Well, I'm going to just check closure, and then I'm going to prove a theorem which is going to allow us to do only closure without like this inverse and zero element. So is it going to be closed? Well, imagine that we have two vectors which kind of belong to this subspace, like one vector and another one. Since they both belong to the subspace W1, the result must belong to subspace W1, right? On the other hand, since both belong to W2, the result is supposed to belong to W2. So eventually the result of addition is going to belong to intersection of them, because at the same time it belongs to W1 and W2. Well, same is going to happen to scalar multiplication. If you multiply like vector inside of this intersection by a constant, first it's supposed to belong to W1, second it's supposed to belong to W2, just because it at the same time belongs to both of them. The scalar multiplication is not going to change that. Now guys, there is going to be an important theorem about like what we're supposed to check if we want to verify that something is a subspace. So let me move to it, because before I was checking the axioms like closure axioms and negative inverse axiom and zero axiom, but actually do we have to check all of them? Next theorem is going to tell us that basically, guys, we're supposed to check only closure axiom. So let me write it on. Theorem: if W is a set of one or more vectors in vector space V, then W is a subspace of V if and only if and only if, a special way to say this, both directions. There are two conditions. A, U plus V not U plus V. First, we're supposed to say that they are kind of U and V belong to W, then U plus V belongs to W. So if two vectors belong to this set W, then the sum is going to belong. Closure under addition. And U belongs to W, then KU, I'm going to use this scalar multiplication, also belongs to W. Well, actually I'm trying to say that subspace or a subset of vector space can work only as a subspace in a case when it's closed under scalar multiplication and addition. And if it's closed, it's going to be a subspace, and if it's a subspace, it's going to be closed. Well, this direction, like if it's a subspace, then it's going to have these two axioms, kind of working just because this is axiom number 1, and I think this is axiom number 6. So obviously that if it's a subspace, these axioms number 1 and 6 are going to work. Now, how about backward? If it's closed, why it's going to be a subspace? Why we don't need to check like the rest of the axioms? So basically these two conditions are axioms 1 and 6, but we have 10 axioms, right? How about axioms 2, 3, 4, 5, 6, 7, 8, and 9, and 10. And I'm supposed to erase 6 because we already kind of set it up. So let me erase 6, okay? How about all these axioms? Are they going to automatically work? Well, axioms 2 and 3 and axioms 7, 8, 9, and 10 are going to work because this is arithmetic which is inherited from mother space V. So just like if vectors follow that arithmetic in space V, they are going to follow it everywhere inside. And for that subset, they are going to follow it. The only two suspicious axioms are axiom 4 and 5. Axiom 4 tells that we do have 0. And axiom 5 tells that we do have inverse in this subspace. Are we going to have it? So basically, what if we have everything is working, but actually 0 does not belong to that subspace? Subspace doesn't have 0. Remember, according to axiom 4, it's supposed to have 0, right? Which you add to any vector and vector does not change. How we can show that 0 is going to belong? Remember in last section we had a theorem, and I'm going to just shortly write it down. And theorem was telling us from 4.1, the theorem was telling us that any vector multiplied scalarly by 0 is going to be 0 vector. And there were like 4 different like subparts, but let's kind of stick to this one. That's one of the part of the theorem. Well, if closure axioms are working, I'm going to use this property to show that it's going to have 0 then. If closure axioms are working, then like K by U is going to belong to W. But let K be equal to 0. Then 0 by U, it's supposed to be 0, but on the other hand, it's supposed to belong to W just because all of them belong to W. Then this one is going to belong to W. So 0 belongs to W. So basically we used that theorem to show it. How do we kind of check for inverse? I'm going to use a part from the same theorem. So that was part of the theorem, right? Another part of the theorem, again from the very same theorem of 4.1, was that -1 scalar multiplication by U, it's actually inverse of U. That was one of the things we proved. Well, I'm going to kind of prove the same way. I'm going to say, okay, K scalar multiplication by U belongs to W. Let K be equal to -1. Then -1 scalar multiplication by U, which is actually minus U, which we proved, right, is going to also belong to W. And we do have that like inverse which belongs to W. So we kind of proved this 4 and 5. So from now on, guys, to check if a subspace is actually a subspace, we're going to just check closure axioms. We are not going to check all other axioms. Okay, now let's talk about some special subspaces. There are many subspaces, guys. I would like you to go through subspaces described in the book, because they are important subspaces and people are using them in math. For example, subspace of continuous functions, or subspace of polynomials, subspace of certain matrices. I don't have time to explain all of this. I'm going to just point at two special subspaces. And first of them is going to be zero subspace. Zero subspace consists out of just one element, at zero element. But is it closed about addition, under addition? So if I add 0 to 0, what I'm going to get? Well, 0, because 0 to any element is going to give the same element, so it's going to give me 0. If I multiply any element, any number by 0 vector, I know from the very same theorem I had over here that it's going to be 0. So, well, these two axioms are telling us that the subspace is closed under addition and scalar multiplication, then it's a really subspace. Okay, next interesting subspace is going to be solution set of all homogeneous, solution set of homogeneous linear system. So that's going to be a theorem. The solution set of a homogeneous linear system AX equals 0 in n unknowns is a subspace of Rn. How do we kind of show that it's subspace? Well, we just need to show that it's closed about addition and multiplication, right? So I'm going to do this. Consider two solutions, x1 and x2. If their solutions mean that ax1 equals 0 and ax2 equals 0. Well, just because they are solutions, they are turning the equation into a true statement, right? How about x1 plus x2? Here, guys, it's just regular addition between vectors. It's like going to be our operation, because for Rn, our operations are just vector addition and scalar multiplication like we usually understand them. So if I apply my matrix A to the sum, what I'm going to get? ax1 plus ax2, which is going to produce 0 plus 0, which is going to produce 0. So ax1 is going to be also solution. So I'm going to write down x1 plus x2 is a solution 2. Okay, good. Number 1. So it's closed under addition. If you have two solutions and you add them, you are still going to get a solution. Closed under scalar multiplication. If I apply A to kx1, let's consider x1 as a solution. If I apply A to this scalar multiplication, what I'm going to do, I'm going to take constant outside of the matrix, which I can do, and I'm going to get ax1, which is equal to 0. So I'm going to k 0, which is going to produce 0, solution 2. So, interestingly, that's also going to be a solution. There are, again, more vector spaces, but just vector subspaces. Just look through them in the book, because like they have nice examples, but if I go over all of them, it's going to take me an hour. Remember that to verify that something is subspace, we'll need to make sure that it's closed under parent or mother operations, addition and scalar multiplication. And that's going to be the only thing to verify. Okay, very short section, and kind of I used today a different method of recording it. Let me scroll it down. Let's see how it's going to work.